Good afternoon, everyone. I'm Likang Zhang from USTC, and today I'm going to present our recent work on experimental pairing QKD with commercial lasers that can surpass the repeaterless bond. So I will first introduce the background of long-distance QKD and, of course, the pairing protocol. Then I will introduce our experimental setup, our frequency tracking scheme, and the key results. At last, I will provide a brief comparison between the two protocols, pairing and twin field, or for long-distance QKD, before I summarize my talk. So first, I think extending the distance of QKD has been a long discussing issue because quantum signals cannot be cloned perfectly, which provides the security but also hinders the distance because of the channel loss. And the repeaterless rate loss scaling provides that the all point-to-point QKD protocols scales linearly with the channel transmittance, including BB84, a continuous variable QKD, and even MDI-QKD with a third-party measurement node. So the proposal of twin-field QKD, which I believe you all know, that improves the rate loss scaling to square root and using the single photon interference, and the fiber-based QKD has been extended to even 1,000 kilometers. But the problem is that the single photon interference in twin field requires the global phase difference knowledge. So it is usually fragile to phase noises of the system and environment, and to achieve high visibility single photon interference, we need to apply multiple phase locking techniques to the system, and which often requires complex and dedicated techniques and may require additional resources. So there's another protocol that is proposed recently called pairing QKD, which generalize MDI QKD and improve the key rate. So in the original MDI QKD protocol with time-being encoding, the keys are encoded into the relative phase difference between two adjacent pulses, and it requires the coincidence detection of the predetermined pulses, so the key rate still scales linearly with the channel transmittance. And in pairing, things got different because the pulse pairs are post-selected rather than in predetermined places. So we can post-select the pulse pairs after the detection results are announced. And if we can use all the pulses that would be wasted in MDI-QKD, we can achieve a great key rate improvement to scale square root of the channel transmittance. And since it is based on two-photon interference, we won't need global phase locking as in twin-field QKD. Since we need to pair all the pulses in pairing protocol, the pairing length will be a very important parameter. And there are two extreme conditions. For the first one, if we limit the pair length to only one, it reduces to the original MDI-QKD protocol, and the key rates still scales linearly with the channel transmittance. And on the other extreme, if we can successfully pair all the detection events, the key rate will scale. There will be an improvement. And so in reality, we can't often pair all the detection clicks because the phase noise of the system will affect the visibility of the two-photon interference when the pair pairs are too far apart and the pair lengths are too high. So normally a longer pairing interval will suffer from a larger phase fluctuation and of course a larger error rate. So for the first two more pairing implementations, there are two directions. One uses commercial lasers, but the relatively high phase loids limited the maximum pairing length to 2000. And the other one uses ultra-stable lasers with very low noise, and which enables a higher key rate and a longer distance. If we place the key rate result in one figure, it's clear that the more pairing provides very much key rate improvement than the original MP-QKD implementations. And we can still see there's a gap between the two implementations using different kinds of lasers. So the next question is how can we bridge this gap and use commercial lasers to achieve a better performance? So first we need to look back to the phase difference which determines the two photon interference. There are two parts of the phase difference. For the first part, it is the non-zero bit frequency between the two independent lasers, and the second one is the residual phase noise. So for the first one, we use a frequency tracking scheme to estimate the frequency in real time and compensate it in the post-processing. And for the second one, we develop a theoretical model to analyze the effect of it. And our system setup is like this. This is very much alike to traditional MP-QKD systems with independent lasers, modulators, and a central node with single photon detectors for measurement. So let me first introduce the frequency tracking scheme. So the core idea is to estimate the frequency based on the single photon detection results in real time. So this is doable because the detection probability of the detectors are acting as a function of the phase difference. So we can use algorithms such as Fourier transformation to obtain the spectrum of the phase evolution from the detection results. And to attain enough detection clicks in a small amount of time, we add the reference frames with strong light to the column frames which are used for key generation. And normally, we would expect the spectrum to look like this, with the maximum part being the bit frequency. But we actually want to use multiple R frames to estimate one frequency to improve the frequency estimation accuracy. This will also bring a sideband problem because the R frames are periodic. And to solve this, we use a very simple strategy that we know the frequency difference between two lasers will change continuously during time. So we select the multiple max amplitude components, and we post-select the central part of the components to get the right frequency element and improve the estimation accuracy. To see how our frequency tracking scheme go, we compare the experimental error rate results with and without frequency. So if we don't apply the frequency tracking scheme, the non-zero bit frequency between the two users will cause the phase to evolve over time, and the error rate will oscillate between 25 and 75%, which will severely limit the maximum pairing time interval that we can accept. So after applying the frequency tracking scheme, we can compensate it and post-select the phases around 0 and pi so that we can reduce the error rates to nearly ideal and at relatively short time intervals. And when the pairing time intervals increases to some point, the residual phase noise include the laser line width and channel fluctuation will accumulate and cause the error rates to increase to 50%. We also develop a theoretical model to analyze it, to give guidance on the parameter optimization and system performance evaluation. And the right dashed line shows our theoretical simulation results, which is a great match with our experimental results. And based on this model, we can further simulate the error rates and even the secret key rate at different scenarios with different laser line width and pairing length. So we can finally get a threshold parameters for the system to surpass the repeaterless bound at about 400 kilometers. So the laser line width need to be less than 800 hertz, and the maximum pairing length need to be over 25,000. And finally, we implement the more pairing protocol using our setup, and we successfully achieve 3 times of the repeaterless bound at 403 kilometers standard fiber channel. And there's a clear improvement over previous more pairing implementations, also with commercial lasers. Okay, I have been talking about more pairing protocols for a while, and we actually have another alternative approach to solve the global phase locking issue with the twin field QKD. So we can use the no phase locking scheme of the twin field QKD without. So the idea is similar. We can construct the global phase reference during the post-processing by estimating the frequency and phase using the single photon detection results. And since these two methods are similar and we have two solutions, a lateral question would be what's the difference and which one would be better in different scenarios. So at the end, I will give a short comparison between these two. So the biggest difference lies into the different mechanism. MP-QKD relies on two photon interference, and twin field relies on one photon interference, which leads to the following difference. I will just skip to the direct key rate comparison. So the pairing in more pairing will make the error rates varying on the different distances, and so the more pairing will suffer from a lot at long distances, but very little at short distances. That's why it can perform better than twin field at relatively short distances. And twin field has the advantage of no pairing, so the effective events will be more than more pairing at very longer distances. So there are advantages of them both at different scenarios. And since they share very similar hardware setups, you can actually change the protocols you are deciding to use only to changing the post-processing and modulating procedure instead of the whole hardware setup. Okay, I will have a quick summary. So we demonstrate high performance more pairing QKD based on commercial lasers, which surpasses the probe bound. And this kind of setup can support chip scale integration, and it's a good solution for future scalable quantum communication networks. And in future directions, I think it would be good to combine such protocols to quantum repeaters to enable longer distance QKD implementations. Thank you, that's all.
Thanks for the speaker. Questions welcome.
Thank you for the nice talk, very clear. In your slide before this one, you show more or less more than 1 order of magnitude difference at 0 dB between the 100 kilohertz TF and MP protocols. At 0 dB, you have more than one order of magnitude difference in the secret key rate between the two protocols. Can you give me an intuition as to why this happens?
Yes, that's a very good question. So for more pairing, when the channel loss is very low, the average pairing interval will be very short, and the phase loss impact will be relatively low, and it won't affect the key rate much. But for twin field, since there's low pairing, and the phase noise is actually affect the error rates and key rates across the distances and losses at a consistent rate. It affects the key rate at 0 or 20 or 40 dB channel losses very likely. So the key rate of twin field QKD will drop as much at 0 dB loss.
But at 0 dB loss, the phase noise should be very small, right? The QBR should be very small. And also in MP-QKD, you have two detectors that have to click. You have a double click rather than a single click in TF. So you have detection efficiency squared in MP-QKD rather than just the detection efficiency of your detector. So for example, let's say if the detection efficiency is 10%,
okay,
I would expect QKD to be about 10 times better than MP-QKD. Is that right?
I'm afraid not so. If we said, actually the effect of phase noise is different from the effect of channel losses. So for more pairing QKD, even if the detection efficiency is low, you okay. Okay, I think this one is better. So for more pairing, when you have a relative low loss, you can set the maximum pair length to a very high value, and nearly all the detection clicks can be paired. So that would be eta divided by 2. It's still, I'm sorry, square root of eta divided by 2. That still scales square root of eta. And for twin field, it's single clicks, valid events, so it scales the same, square root of eta. And that won't cause a very a great difference between the two protocols.
Okay, I must think about that. Thank you.
I can explain it after this talk.
Yes, sure. Thank you.
Yeah, I just want to answer Marco's question, because at 0 dB, we simulate the laser with a very bad or very long linewidth, 100 kilohertz. So even at 0 dB, the two laser is unlocked. If you don't lock a laser, at 0 distance, if you do TF-QKD, still have very much phase noise. That's why at 0 dB, TF-QKD have a higher quantum bit error rate. So that's why it's lower. But if you have a better laser, like ultra stable laser, then you don't need to do any locking. You already have very slow, very small phase noise. I think that's the fundamental reason you have 1 order of magnitude difference.
Okay, I have a question. So, what is the limitation for your setup to achieve a longer distance, maybe 500 kilometers or longer?
Okay. So the first improvement would be the clock rate, which can improve the final key size, and also we can use a larger maximum pairing interval. And also we can use lasers with lateral line width, if there's one, which can give us a smaller error rate and boost the distance. Yeah, I think that's all.
Okay, thank you. If there is no other questions, let us thank the speaker again. Okay, thank you.